Welcome! In this video, I will show you how to solve problem 4.14 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem states the following. It says, use the recursion formula, which is equation 4.76 in the book, to confirm that when L is n-1, the radial wave function takes the form that we see right here, and we want to determine the normalization constant by direct integration. We then want to calculate the expectation values of r and r squared for the states of the form when L is n-1. And then we want to show that the uncertainty in r is going to be of this form. And we will then, analyze it a little bit. So what this problem is, it is a nice way to get a bit more acquainted with solving the radial equation and understanding the solution itself, right? So we're going to just be working with the radial solution to the hydrogen atom, to the hydrogen potential. And here, of course, we are not really going to care much about the angular part. You will see why. And yeah, this is just going to help us get acquainted with the recursion formula. If you don't really know where that came from or what they mean by that, the recursion formula is what we can see right here, then I recommend that you go watch the video where I derive it in the description, because even though it is usually not necessary for you to know by memory the recursion formula or how the process is done, it is important that you understand how to use it. So you have to at least have done the process just at least once, right? So as always, I encourage you to pause the video and try to solve this by yourself. And if you have any issues, then come and see how it is done and then go back. Okay, so don't just take the answer from me. Try to do it. When you get stuck, you come, or you just come to check the answer as you wish. Okay, so before we can begin, we need to remember a few things. So the wave function for the hydrogen atom is given, of course, by the product, because we did separation of variables, of the radial part that will only depend on the variable r, but depends on the quantum numbers n and l, and the angular part, right, that depends on theta and phi, and on the quantum numbers l and m. Now, the radial part is given by this equation right here that we have already derived in the past. Again, link in description if you want to see it. 1 over r, and rho here is simply r over na. That also comes from the whole process that we did when solving this. And here we have this v of rho. Now, this is very important because this is where people tend to get confused. This v is a polynomial of degree j max n minus L minus 1 in rho. What does that mean? That simply means that v of rho is going to be something like a0, some coefficient. Why a0? Well, a because it's some constant, right? And 0 because, well, that's the term that accompanies rho to the 0th power, right? Then we have a1 rho to the 1 plus a2 rho squared plus a3 rho cubed, and so on and so forth, all the way until some a of j max, rho of j max, right? This is what we meant. We said a polynomial of degree j max, and this is it. Now, how do we know the maximum degree? Well, for that we can go here to this recursion formula, because this recursion formula gives us a0, a1, a2. Right? Why recursion? Because, well, we start with the lowest case, which is a0, and then we get all other coefficients, a1, a2, a3, a4, etc., in terms of a0. Okay, so that's why it's recursion. It kind of goes back on itself all the time. Okay, so with this now, we want to solve this case. However, as we will see, we are interested in the case where L is equal to n-1. And by the way, it's quite important here to keep in mind, how do we know what the maximum j is? Well, we simply know it because at some j, this thing here is going to be 0, right? Because we can't have an infinite polynomial. We can't have an infinite polynomial, right? You are not going to be able to integrate, to normalize that. It's not going to be normalizable. That's one of the conditions that we saw when solving the radial equation. And to find the maximum, we just simply set this thing equal to 0. So j plus L plus 1 minus n is equal to 0. That's the case for j max. And from here, you can see that j max, it is going to be n minus 1 minus L, which is, of course, exactly what we had before. So that's just so that you have an idea where that condition came from. And also that you know that that condition is basically the same as this if you want to find the maximum, you can either use the condition or just use the recursion formula until you get to the condition. Okay, so now let's actually begin part A. So just a quick reminder. So we wish to use the recursion formula to confirm that when L is n-1, the radial wave function takes that form. Okay, so we need to find the polynomial, and for the polynomial, we need to find the coefficients. So let's begin with A1, right? When j is equal to 0. So when j is equal to 0, I told you, right, we start at the lowest point. That's why it's a recursion formula. We start from the base case and then work our way up. So this is 2 times 0, which is j, plus L. But what is L? We said L is, let's take a look at it, or rather, yeah, L is n-1. So instead of L, we write n-1. And then we have plus 1 minus n, A0, and j plus 1, j plus, now instead of 2L, we have 2n minus 2. But honestly, it doesn't really matter at this point because as you may have seen already, n-1, we have plus 1 minus 1 plus n minus n. So this entire thing is actually 0. So what this means is that the maximum j is actually 0. So we only have this part. Everything that comes after is 0. Right? We could also have found this by going to this condition, seeing, okay, what is my maximum j if my L is n-1? So we have n minus n-1 minus 1. So we put this minus through. So in that case, we get minus n and plus 1. And here again, we see, well, n minus n, 1 minus 1. So we get to the same condition as expected, of course. So that means that our polynomial is simply this, right? It's A0 times rho to the 0. But rho to the 0 is 1, so there's no real need to write it down. So with that in mind, let's now write our radial function for n and the case where L is n-1. So let's write it as Rn n-1. Now, of course, you don't have to write it like this. This is simply a nice nomenclature so that you understand visually and others can understand what it is that you are doing. That's always very important. You don't only write for yourself, you also write for others to understand you. That's a key part in science communication and science overall. Science is communication. Okay, anyways, so this is 1 over r. I'm simply going through this formula right here. Now rho to the L, but what is L? It is n-1 and plus 1, right? Because there was a plus 1 right here. And e to the minus rho, and now our polynomial, which is simply A0. Now, let's use the fact that rho is r over na. So that we have 1 over r, and then, well, n minus 1 plus 1, that's simply going to be rho to the n. And now we plug it in, so r over na to the nth power, and then e to the minus r over na and A0. So here we can do a few simplifications, not too much, but we can write this as A0 over na to the nth power. And we also have r to the n-1, right? So basically combining this r with this r right there. And we still have e to the minus r over na. So this is the radial part. So r to the n-1 of r, right? We wanted it in terms of r, not necessarily in terms of rho, which is just a variable that we introduced to make calculations easier when we solved the radial equation. So this is now the first thing that we wanted to get to, right? So kind of, we have r to the n-1, e to the minus r over na. So there's a little bit of a difference. So let's go and fix that. Because instead of having A0 and this, what Griffiths did is just introduce a new name. So they said n, that depends on small n, right? The normalization constant, that's what the big N is for. That depends on the quantum number, small n, that's a bit confusing. This is A0 over na to the n. So if we do that, this here is simply n to the n. And you can see that we did arrive at the exact same formula, which is, very nice. But now we still want to determine this normalization constant. And they told us to do it by direct integration. So that's pretty straightforward. Again, try to do it yourself before you watch the video. So what this means is we have to say, okay, so 1 has to be equal the integral over all of space of our wave function. Now, keep in mind, the wave function has to be separately normalized. So what this means is that we are actually integrating from 0 to infinity, and also from 0 to 2 pi, from 0 to pi, and we are integrating our wave function squared, r squared, sine theta, and here we have, well, d theta, d phi, dr. And what we can do here, of course, is just instead of having this, we plug in r and the spherical harmonics, right? We simply plug in this combination that we have here, right? We did separation of variables, that's all we did, and we separate the integrals. So by doing this, we are simply saying, well, 0 to infinity, r squared dr, and then we have the integrals that concern the angles, right? So we have 0 to 2 pi, 0 to pi. I'm not sure I put this the angles d theta, d phi in the right order, but it doesn't matter. We're not going to integrate them, but keep in mind. So that's this squared sine theta, d phi. And this thing has to be 1. And we know it is. We know that spherical harmonics are already normalized. We have done it before. And for this thing to be normalized, this also has to be 1. So both of them have to be 1 separately. So this, of course, is already 1. That's why we end up with simply this equation. So you could have just gone ahead and written down this equation. You didn't have to go through all this previous step that I just did. I just wanted to make very sure that you understand why we are not writing down the spherical harmonics. Okay, I just wanted that to be very clear because that's already 1. And the rest of the condition is that the radial function also has to be 1. Okay, so that's it. I hope that cleared things up. So now we just plug in our formula. So we're integrating from 0 to infinity. And now what is r squared? Well, it's this thing squared. So we have n squared r. Now this thing squared, that's going to be 2n minus 2. E to the minus 2r over na r squared dr. So we have r squared and we have this thing. So we can add the exponents. So we get simply r to the 2n. And now this constant nn doesn't depend on r. So we can just take it out of the integral. So we have 1 equal to the integral. So, and in front we have nn squared, 0 to infinity of r to the 2n e to the minus 2r over na dr. Now, this integral is one that you're going to solve so many times. It is such a common integral. It is so common indeed that I made a video about how to solve it because it pops up all the time. Now, the way to solve it is to use integration by parts. So you say, okay, u is equal to r to the 2n, du is going to be 2n r to n minus 1, dv is going to be e to the minus 2r over na dr, and v is going to be minus e to the minus 2r over na times na over 2. Okay, and then you do integration by parts, yada, 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 and you will have to do it many times over. In fact, like 2n times, which is not very fun. So that's why I made a video where I teach you a nice formula. So whenever we have an integral that is of the form 0 to infinity of r to the a, let's say, and e to the minus br dr, this is simply going to be a factorial, and then we have to multiply this by 1 over b to the a plus 1 power. Okay, so where did that come from? Again, the link to the video is in the description. I do recommend that you learn this because, again, this integral pops up so often that you really do, trust me, you want to learn that. Okay, and if not, learn how to derive it, it's very quick. Okay, so using that formula here, in this case, A is 2n and B is 2 over na. So that means a factorial is simply going to be 2n factorial. Of course, keep in mind, we still have this n squared. And then we have 1 over b to the a plus 1. But b is 2 over na, so 1 over b is going to be na over 2. And this is to the power a plus 1. But again, what is a? A is 2n, so this is simply 2n. There we go. And this, of course, has to be equal to 1. So from here, we can quickly find n squared, which is going to be just 1 over this, right? We are simply doing some algebra here. So 1 over 2n factorial times 2 over na. And this is all of this to the power 2n. Actually, I don't like that parentheses there. 2n plus 1. And we now can just take the square root. So we find n. So we get, let's see, 1 over the square root of 2n factorial. And then we have, now the square root is the same as multiplying the exponent by 1/2. So we have 2 over na. And this would be n plus 1/2, right? We multiply this thing by 1/2. That's what we did. And with that, well, we can do just a little bit of simplification because we can separate these exponents as 2 over na to the n and 2 to the na to the 1/2, which is the square root. So by doing that, we get 2 over na to the n, and then we have the square root of 2 over na times 2n factorial. Okay, and that is the normalization constant. So if you know what n is, 1, 2, 3, whatever, you can just plug it in and you will find your normalization constant very quickly. So that's very nice. So what we just did again is find just our general formula, right? If you want to find the normalization constant of a wave function or of a state where L is equal to n-1, you can use these formulas. You can use this formula right here, where the normalization constant is what we just found down here. So that is very, very, very useful. Now, part B asks us to find the expectation value of R and R squared for states that are of this form, right? So let's go for that. So part B, we want to find the expectation values of R and R squared. Now, it is quite important to note that we are going to have integrals that are of very similar form of what we just found, right? So let's see. In the case for R, the expectation value of R is going to be integral from 0 to infinity. Again, in principle, we're integrating over all of space, but our radial wave function doesn't really include theta or phi. So the angular part is going to be normalized. Again, I guess I can show you that again. So 0 to 2 pi, 0 to pi. And then here we have, this would be R squared, the angular part squared, right? The spherical harmonics. And of course, we need to multiply this by R because we are taking the expectation value of R. So that, of course, goes in there. And then we have R squared sine theta, and then we have dr, d theta, d phi. Now we can separate the integrals because again, the spherical harmonics don't depend on R and the radial part doesn't depend on theta or phi. So we get integral from 0 to infinity of R squared, R cubed, dr. And with this, well, then we have 0 to 2 pi, 0 to pi, the spherical harmonics squared, sine theta, d theta, d phi, but this thing is 1, right? The spherical harmonics are normalized, so that thing is 1 again, so all we care about is this part. So again, You don't really have to go through that, but it's important that you understand why we're only looking at this and not at everything else. So this thing right here, just bye-bye, and let's just leave it like this. So just select it and let's just move it quickly. So now let's just plug in what R is. So we have it written over there. So we can just take the normalization constant out of the integral. So that's n squared. We integrate from 0 to infinity. And then we have R to the 2n minus 2 e to the minus 2r over na. And then keep in mind, we still have these r's right there. So we have r cubed dr. So what we end up with, right, we have to now add the exponents for the r. So 2n minus 2 plus 3. So simply 2n plus 1. So 2n plus 1. And now in the case for r squared, we're going to get the exact same thing, because the only difference is that now we're multiplying by r squared instead of r. So we are going to get the same thing, but now the exponent of r will be 2n plus 2. That's it. That's the only difference. Okay, so those are the two integrals that we are going to have to solve, and look at them. They are of the exact same form of what I told you we would encounter all the time, which is exactly that. Okay, so let's use that formula. So using it, again, if you don't know where it comes from, the link is in the description of the video for how you can solve this integral. So this is now n squared, and now we multiply 2n plus 1 factorial, and then we times 1 over b, right? To the, in this case, it would be 2n plus 1. So b is na over 2, and this would be 2n plus 1, but plus 1 again, right? Because what we had was a plus 1. So if a is 2n plus 1, we end up with 2n plus 2. Okay, so that's that. And in the case for the expectation value of r squared, we are simply going to get n squared. And now we are going to have 2n plus 2 factorial. So 2n plus 2 factorial times, now this is going to be na over 2, 2n plus 3. So that's the main difference. Now we can plug in what we found for n. Now, of course, we have it squared, so it will be much easier to just plug in this part right there. So let me maybe change colors. So for the expectation value of r, we plug it in, and we have 1 over 2n factorial. And then we have 2 over na to the 2n plus 1. And now we multiply by this. So we multiply by 2n plus 1 factorial na over 2 2n plus 2. So here we can do a little bit of a simplification. All right, so we have 2n plus 1 factorial divided by 2n factorial. That is simply 2n plus 1, right? Because this is 2n plus 1 factorial is 2n plus 1 times 2n factorial. So the 2n factorial would cancel out with that one, and you are left with 2n plus 1. Okay, and I just noticed that this parenthesis is in the middle of my number. Okay, so we dealt with this and this. Now we have this 2, which is to the 2n plus 1, and that is divided by 2n plus 2. So we're going to end up with 1/2, right? This one survives. And similarly, we are going to be left with na. So here we're going to have na, right? That's when this part cancels out with this, and the 2 with this. So here we can just multiply through by 1/2 if we want to simplify this just a little bit more, and we get na n plus 1/2. So that's the expectation value of r for wave functions of this particular form. Again, it isn't valid for every wave function. It's only for the case where L is equal to n-1. So for example, it would be valid for psi 2, 1, and any m. For example, it would be valid for this, but it wouldn't be valid for something like 2, 0, and m. Well, in that case, it would have to be 2, 0, 0, of course. And it isn't valid either for 3, 1, for example. It's not valid for that either. So keep in mind the limitations of what we are doing. Now we do the same procedure, but down here. So we plug in n squared. So in this case, we have, again, 2n factorial. I guess I should have put a parenthesis there to be more explicit, but then 2 over na, 2n plus 1. And now we multiply by this thing right here. So that's 2n plus 2 factorial na over 2n plus 3. So this is very similar to what we had in the previous case, but now we're just going to have more leftovers. So for example, 2n plus 2 factorial, so 2n plus 2 factorial, this is simply 2n plus 2 times 2n plus 1 times 2n factorial. So like before, we can simplify the factorial with the 1 down there, and we're left with 2n plus 2 and 2n plus 1. Okay, so that's quite important, and that's going to get rid of this and this. So I always like to mark what I have already considered so that I don't write anything additional. Then we have 2 to the 2n plus 1, and the same thing as before. So we're going to be left with a factor of 1 over 4 and na squared. All right. And here, like before, we could go ahead and multiply through by 1/2 to each one of these because we have 1/4, which is 1/2 squared. So we can write this as na squared times n plus 1, right? We multiply this by 1/2 and we multiply this by 1/2, so we get n plus 1/2. And there we go. We found the expectation values for r and r squared for wave functions of this form. Now in part C, what we want to do is show that the uncertainty in r is going to be the expectation value of r over the square root of 2n plus 1, and we will then analyze it a little bit and sketch some radial wave functions. So, part C, here we have, we want to find the expectation value, the uncertainty in r. So how do we find the uncertainty? Well, here we have r squared, right, the expectation value of r squared minus the expectation value of r squared, and this inside of a square root. All right, and here we have to keep in mind a little bit of a something. Sometimes you forget. It's like, oh, what comes first? Is this expectation value of r squared minus r squared? Which one is it? Now, this one is not 0. That's not going to be 0. Right? Sometimes you can get that the expectation value of r is 0. And that is okay, because if that happens, you end up with a positive number inside of the square root. But if you take the second formula, right, if you take this, and it just happens that this thing here is 0, you're going to end up with a minus inside of the square root. And that is, of course, unacceptable in this situation. So that's kind of one way in which I think about it. I know that sometimes the expectation value of x or of r or something can be 0. And that's how I think about it. Okay. Anyways, so let's now plug in our results. So this is the square root of r squared, the expectation value of r squared, which is that thing over there. So this is na squared n plus 1 n plus 1/2 minus the expectation value of r squared. So that means 2n, let's write it a bit more, 2n plus 1 squared. Actually, sorry, I was copying the unfinished version, so that one is cleaner. So we have n squared a squared, or maybe to keep the same notation, na squared, and then n plus 1/2 squared. Okay, so this thing that we have right here, well, let's factor out na squared. We can take it out of the square root and it turns into na, And we also have inside the square root, we can factor out n plus 1/2. So we can factor out n plus 1/2. And then we are left with, maybe let's use this parentheses. Then we have n plus 1 minus n minus 1/2, right? Because of the minus that is just before it. So here we get, this would be na square root of n plus 1/2. Now the n's, they cancel out and we get simply 1/2, so 1/2. So that is what we get. But keep in mind that what is being asked of us is to write this in terms of the expectation value of r. So, well, we know that this thing right here, this is the expectation value of r. So how could we write this in terms of that? Well, from here, what I would do is just say, well, I have NA here and there. So let's just solve for NA. We know that NA is expectation value of R over n plus 1/2. So let's plug it in here, right? So we can now write this as expectation value of R over n plus 1/2. And we multiply this by the square root of n plus 1/2 times 1/2. So here we can simplify the n plus 1/2 a little bit, right? This is going to be expectation value of R over, and here square root of n plus 1/2 and times 2. So I guess we could write this as the expectation value of R over the square root of 2n plus 1. So that is how we could write this, and we can see that that is exactly what we wanted, right? So the expectation value of R over 2n plus 1. That is the general formula for the uncertainty in this particular kind of wave functions. Now, let's think about it, because this is quite interesting, because as our n gets higher and higher, right, as we go into the higher bound states, then we get that our spread is going to be smaller and smaller. The uncertainty is going to be smaller and smaller because n is increasing, right? The bigger n is, the smaller the uncertainty is. So we can think about this by just graphing a few wave functions. So let's go for our general formula. So our formula for R, I already lost it. Where did we put it? It's right here. So we can just take this and just very, very quickly sketch a few of these wave functions. So if we want to sketch this, maybe let's just quickly find the maxima for this function. So we can just take the derivative of our general R, right, Rn n minus 1, with respect to R, and set it equal to 0. So if we do that, we have, well, of course, our normalization constant, and then we have n minus 1 times Rn minus 2 e to the minus R over Na, and then we have plus the derivative now of this, right? It's the product rule, so plus normalization constant Rn minus 1, and now minus 1 over Na times the same exponent. So this has to be equal to 0, and that means, of course, we can go ahead and just divide by this exponent or multiply by the inverse of the exponent, because that's not going to be 0, so that's not really any of our concern at the moment. So we get rid of that. We can also get rid of this normalization constant. It cannot be 0, so we don't really have to worry about it at all. We can also get rid of some of these r's, right? We have r to the n minus 2, r to the n minus 1. So we could, here, for example, just divide by, let's say, r to the n minus 1, for example, so that we get rid of this r n minus 1. So we have r n minus 2 minus n plus 1. So by doing this, we get rid of this n, and we are left with r to the minus 1. So we are just doing here some algebra so that we can find the r at which we are going to have the maxima here. Or, well, it's of course going to be the turning point, but we know it's going to be the maxima here just because of the overall shape. But it's just going to help us sketch. You could, of course, take the second derivative if you want, but we don't really have to go into that. So here we solve for r, right? So we have r to the minus 1, n minus 1. This is going to be 1 over na. So to solve here, we get that r is going to be na times n minus 1. Okay, so this gives us the place of the maxima, which is really going to help us sketch our graphs. So we can now begin, let's say, of course, with the most basic case where we have, so R10. So let's go for R10. So that is the most basic case. In that case, we have our normalization constant, which we don't really have to care about. It only fixes your position, but we care about the shape itself. We are just sketching here. So then we have r to the 0, which is 1, so no need to worry about it, and e to the minus r over a. So that is going to be our radial function 10. So this is simply an exponential that's decaying somewhere over here. And according to this, if n is equal to 1, the maxima is at 0, which of course makes sense. It's falling exponentially all the way from 0, which is the maximum value, where its value is whatever this normalization constant is, which we could actually find. Of course, we have the formula for it. We could just plug it in here, but honestly, we don't really care that much. But you could do it. Now, this graph is, of course, in terms of r. I guess I should have written it down a bit sooner. Now we can go for some other graph. For example, let's go a bit higher. Let's go now R32. Keep in mind, this is not valid for all wave functions. Don't forget about that. So R32, this is going to be the normalization constant. And then we have n minus 1. So r to the 2, right? R squared, e to the minus r over 3a. So now here, you could either plug this, I guess, into a programmer if you want, or just if you know what the overall shape of such a curve is, we can find the maxima again, na, so that is 3a times 2, so 6a. So our maxima is here at 6a, and the curve is just going to be something like this, right? And then if you go way higher, like, I don't know, like 101 and 100 or something like that. So we go R100 and 1, 100, right? So we are way higher here. This would be the normalization constant, r to the 100, e to the minus r over, and here we have over 100 and 1a. So, well, quite a number here. So the maximum here, using our formula, would be 100 times 101 times a. And I don't really feel like calculating that, even though it's got to be close to 10,000, I guess. 10,100. But I guess I don't want to make a mistake here, and it doesn't really matter. So 101, 100 in terms of r. And now this is just going to be even more like this. So it comes all the way here, it has a bump, and then it goes very small again. So this is the overall shape. And as you can see here, the situation is indeed what we expect, right? The larger it gets, the more pronounced it's going to be. It's going to be more and more localized. It looks more and more classic, right? It's not all that spread out. It's becoming more and more localized. And that's, of course, because we're going to higher energies as well, which is what we expect when we expect to get to the classical realm. So there it is. That's what was asked of us, right? We sketched the radial wave functions for several values, and we illustrated that it began to look classical because the spread was getting smaller and smaller. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.